Let's talk about now objects on a plane that's actually at an angle here. So a ramp, basically, or anything else, any other surface that is tilted at an angle, not perfectly flat according to the Earth's surface. So if I have a ramp here at a 15-degree angle and someone is trying to push a piano up, for example, moving into a new house that they just bought or whatever it might be, you're going to have, whenever we label the forces, everything at odd angles. So you got a force of push going up like this, Fp, right? You have force of friction going directly back parallel to the surface, right? Not back at an angle, parallel to the surface there. Then I'm going to have, check this out, normal force going up, but it's going up perpendicular to the surface. Gravity, though, is the exception. Gravity pulls straight down, right? Gravity doesn't care that you're at an angle. It still is pulling straight down, okay? Because the Earth is always pulling downwards. Whenever we translate that onto an XY axis, I'm going to have force of push up like this, Fp. I'm going to have force of friction back like this, Ff. I'm going to have normal force up like this, Fn, and then I only have one vector on the XY axis, force of gravity. Now, we could, because we know that ramp is 15 degrees, we could suppose what this is and what this is, right, and other angles along those lines. But then we've got to do a little bit of math to get this angle here, and that's not terrible. But check this out. I've got 1, 2, 3 vectors that I'm going to have to divide into components whenever I have an object on a ramp or on any tilted surface. 3 vectors divided into components is a little crazy. Whenever I have force of gravity, that's the only one on the XY axis. Check this out, though. What if instead I tilt the axis? So instead of keeping an upright XY axis, what if I kind of tilt it a little bit? And so I lay it down to where it looks like this here. Okay, so I tilt the axis just a little bit. So now here's my X, and here's my Y. You'll see some college professors will actually lay the Y-axis down in place of the X, but our book doesn't do that, so I'm going to stick with this. Both ways it still works the same. So whenever I tilt the axis, check it out. Now, force of push and force of gravity are on the X-axis, and normal force is on the Y-axis now. In fact, the only thing that isn't on the XY axis is just force of gravity. So let's put all these on a tilted axis over here. Okay, so I've got going directly up in my tilted axis, normal force, right? Perpendicular to the surface, right? And let's actually get a nice perpendicular guy going there with normal force going up. I'm going to have force of push going what I'm calling positive in my x-axis. I'd have force of friction going backwards there. And then gravity would be the one outlier going straight down, okay? He'd be the one outlier, and the one guy I'm going to have to break into components. So the next XY axis down here, remember we do 2 free body diagrams. If there is any vector that's not on the XY axis, the reason we do a second free body diagram, it's the same as this one. I just need to now break this force of gravity into components so I can, obviously write my sum of the forces in the X and the Y. So I have normal force going up. That's unchanged because it's already on the X-axis or on the Y-axis. I have force of push. I have force of friction. And then I'm going to have gravity. I just got to figure out how do I divide this guy into components. So let's talk about that. Look at, if you will, this picture up here. So I have some angle of a ramp. Now, angles of ramps are pretty easy to measure because you can actually take a protractor to it. Okay, so that's not bad. Let's say this angle is, 30 degrees here. The angle that I'm going to need to check out, all right, is I'm going to try to get around to this theta here, and we're going to look at this triangle right there, where force of gravity is the hypotenuse, okay? Here's my x component of that triangle, what's going down the ramp. Here's my y component, what's going into the ramp, all right? So I'm going to try to divide this into a x component of gravity, right, which then can be slid up onto the x-axis, and a y component of gravity. So this vector divided into that right triangle here, all right? So now think about this. Notice this right triangle, okay? If this is 30 degrees, that means this angle right here is 60 degrees, all right? Because it's a right triangle, right? 180 degrees, 90 degrees taken up right here, so 30, 60. Wonderful. Now, check this out. So here's the right triangle I'm going for because to get my y and my x components of the force of gravity. But notice this right triangle, okay? Or notice this right angle right here, all right? Between, this is just the x and y axis, right? Here's my right angle, and so 9 degrees, one part of it's 60, leaving this angle back at, once again, 30 degrees. In other words, this is just kind of the mathematical proof. It actually makes life really, really easy. Anytime you're dealing with a ramp, gravity that's going to go down the xy, or down the x-axis, down the ramp, check it out, it's on the opposite side of the angle. So going down the ramp will be the force of gravity sine the angle, and going into the ramp, opposite of normal force, will be Fg cosine the angle. Okay, so force of gravity cosine the angle, which is opposite backwards from what you normally get, right? Here we have the x-axis with Fg sine theta and the y-axis with Fg cosine theta. The reason that we're doing that is, this proof of figuring out this is the angle we're using. Notice this is the angle measured to the y-axis, so then your sines and cosines flip. So we normally don't do that, but this is an angle that's easy to figure out because it's the exact same angle as the angle of the ramp. All this is to say that whenever you're writing down your xy axis, right, and you're dividing everything into components, you just use the angle of the ramp. Remember to flip sine and cosine. So here in this very specific example where I have a ramp and a man's pushing a piano up the ramp, so it is in reverse from this picture, so he's pushing it up and to the right, gravity's coming down, and so the ramp is coming like this, right? I'm going to have here gravity, Fg sine theta going down the ramp, Fg sine theta going down the ramp, and Fg cosine theta, Fg cosine theta going into the ramp. Okay, so that's what's going to end up happening. Normally, you would immediately say, hey, look, all I'm going to use on it's y-axis, I use the vector, force of gravity, sine, and the y-axis. But here, remember, because we're using the angle of the ramp in this little proof that we just did over here, on the y-axis, for force of gravity, you use Fg cosine theta, and for going down the ramp, you use Fg sine theta. So if you need to remember anything, right, and all these proofs and everything else, the grand conclusion behind this is the component of gravity that goes down the ramp, Fg sine theta, the component of gravity that goes into the ramp, opposite normal force, Fg cosine theta. All right, let me work a problem now for you. And this problem works just like any other problem whenever I'm pushing an object. So we're going to push an object. Your brother is pushing a 201 kilogram refrigerator up a 20-degree, notice the decimal, ramp into a moving truck for you to take to college because apparently you're going to have a lot of food in your teeny dorm room now. How much force does he need to push it with to move it up the ramp at constant velocity? Keywords there, right? Acceleration 0. Coefficient of friction 0.10. So, free body diagram of this picture I have going on over here. You have a force pushing up the ramp. You have normal force perpendicular to the ramp's surface. We tilted the axis, right, so that these three vectors all go on the x and y axis, and the only outlier is gravity. So there's only one thing to divide into components. So I have a force push, and I called that way positive in the x-axis, normal force, force of friction going down the ramp parallel to the surface, and then gravity always pulls straight down. So I'm going to have to divide gravity now into components. The component that always goes down the ramp is Fg sine theta. So every time you have a ramp, Fg sine theta is what goes down for the force of gravity, and Fg cosine theta, Fg cosine theta, kind of running out of space there, cosine theta, goes into the ramp opposite normal force. Now I solve this problem just like I would as if it was flat. Okay, I have an x, and I have a y-axis. I write some of the forces, and then I write what I see here, and I solve what I'm looking for. I'm looking for Fp, the force that we're pushing with. So in the x-axis, I'm going to have Fp, force of push, minus Fg sine theta, right, because that's what's going in the negative direction. I called down the ramp negative, minus force of friction equals ma. In the y-axis, I have going up positive y, normal force, Fn, minus what's going down is Fg cosine theta, that component of gravity, Fg cosine theta, equals ma. The only difference from what you're used to is gravity had to be divided into components. Sine theta for going down the ramp, cosine theta for going into the ramp. Cosine and sine are backwards from what you're used to in the x and y axis here. All right, so now I'm just going to work a little bit of algebra. Starting in the x-axis, I got Fp, what I'm looking for, minus Fg always breaks into mass times gravity, so Fg breaks into mg. Now, the sine theta is still there. Force of friction, mu times normal force. And I know this acceleration is 0 because of the words constant velocity, right? So that entire side is equal to 0. Let me jump over to the y-axis and just try to break things down there for a second. Fn minus Fg always turns into mass times gravity. Cosine theta equals, once again, 0 because the object isn't flying up off the ramp or plunging down through it. All right, so I'm looking for Fp. Here it is in the x-axis, so I'm going to just start plugging in numbers and solving down as far as I can there. So I plugged in what the mass was, 201 kilograms, gravity 9.81, the angle for theta 20 degrees. Whenever you do all of that, you get 674.398, so on and so on. Mu was 0.1, and so I'm left with force of push minus what this entire term came out to be there, right? Minus the force of friction, mu times normal force, equals 0, and I go, oh, if I knew the normal force, I could solve for Fp, so I need to get normal force. And of course, every time you say that to yourself, you jump over to the y-axis, just like you normally do, because here's normal force, right? I hit a brick wall, so I jump to the next axis. So let's start substituting numbers in there and solving. So once I substitute numbers in for mg cosine theta, I get 1,852. So normal force is going to equal 1,852.89. Great. Now I can take that and I can substitute that in for normal force. Now it's just a touch of algebra. And after I work all that algebra down of plugging in and multiplying these two, these are both negatives, so they're added together, negative, right? I come out with force of push equal to, with significant figures, 860 newtons needed to push that refrigerator up the ramp. The main thing I want to point out to you in these problems is all of this stuff here is exactly the same for what you're used to of pushing a box horizontally around on the surface. The big difference here is you have this component of gravity and this component of gravity in the y. So really the only difference between this and just pushing a box along a surface is gravity, because at the angle, gravity is at an angle, right, because of the ramp. We had to break it into its two components, Fg cosine and the y, Fg sine and the x. Make sure to tilt your axis to make life easier on you there, and then you just go through everything you're used to.